Okay, so I have made the program C0.c. Now, from CS2, from previous semesters, we could compile 0.c using the regular compiler, and we would get the executable 0. And then if I ran that program, now if I run hello, um, let me just, if I run 0 like this, it seems like nothing's happened, except I can check um, the return value with this weird command. There's a variable question mark which asks, were there any errors when the program ran? And the $sign means get the value of the variable question mark. And then you echo that and you find 0. There were no errors. Okay, now I could change this to have return 0 and it would do the same thing. But I could also put in a value, say here 1. Now 1 means yes, there were errors. I mean, that's an indication of the programmer. There aren't any errors here, but this is just to see that you can get that 1 out. So I compile it again, I run it, then I do echo 0 and I get the 1. So that 1 was returned from the program to the shell and saved in this variable question mark. So then the shell can decide what to do. If there were errors, it might do one thing. If there's no errors, it might do something else. So that's the purpose of this return value. Now, that only makes sense in the context of an operating system and a shell that's going to do stuff with it. We're not going to be doing that. So I'm going to show you first how to, because the LC3 doesn't have all that stuff in it. So we don't need to, okay, let's see, where is, yes, okay. So we have here, let me remove 0, okay? So we have here, let me also remove hello, because those are the actual executables, okay? But what I want to do now is I want to compile this to LC3 assembly language. So in the directory, this you might have, so we're going to then start the text editor. Oh, not here. Yeah, oh no, this is the right one, okay. Accessories, text editor, okay. Then open, and we can go to home, cprog, and we'll open 0.c, okay? But then we're also going to open the make file. You don't have to understand how the make file works. It's just that what you do is you just want to change the name here of this file to the name of the program without the .c. The .c means this is a C source code file, that you want to change the name here after code to 0. Then you see we're going to get the LC3 compiler, and we're going to end up then with instead of the actual Linux compiler GCC, we're using the LC3 compiler. So if I have every time you want to run a new program, you have to edit this make file. So let us, and you'll be doing this a lot, is, let me see if I can get this side by side, where you would have sort of like your program file here, your make file here. Then over here, if you want to compile the file, you type make. And let's see, what did I do? Oh, well, it says, gave me a warning, says 0.c5 warning, missing return value, right? But it said starting pass 1, starting pass 2, 0. Now, this is like just like the assembler was a 2-pass compiler. a two-pass assembler. This is a two-pass compiler in which it first walks through the program to get all the variable names and makes something called a symbol table. Um, and then that enables it to construct the activation record and construct the code. So let's see what this did. Well, if you look here, we have 0.asm, that's the assembly, 0.c, and 0.obj, which is the object file, and 0.sim, which is the symbol table. So now if let's say that if we wanted to run this, we can't run this just from the command line the way we did before. We have to run it from a simulator. Now, unfortunately, the ASM that's produced here isn't quite compatible with our online simulator, and the object file here is already a binary file. So we can't, it's not a file of ones and zeros. It's like, so this goes too far for the online simulator, and this doesn't go far enough for the online simulator. Fortunately, there is a simulator on Vera Virtual. So if I go then to LC3 compiler, then I end up with two subdirectories. So I go to LC3 tools, and I end up here, and I can see here LC3 sim-tk. So I can /LC3 sim-tk. I might have actually given labels to this, so you may be actually able to type this from anywhere. But if I click this, I get sort of an old style. Let me get this out of the way. I have an old style simulator, and it blocks the console, which is a separate window. So what it does is it prints off a message telling you to have fun with the LC3. And so now let's say I wanted to load a file. So I could browse here, and I want to go back then to home, Vera, and then there's a lot of hidden files here. But you can find cprog, and then here's our object file 0, and I open that, and I have here a bunch of assembly code. You can see here, this is initialization code at X3000, and there's a whole bunch of stuff here. It's not too long, but look at this. This is like a whole bunch of lines of so all of this stuff is just for this program. So we've got like almost like 2 lines or almost no lines of C, and over here we have a whole bunch of stuff. And so that doesn't sound very encouraging, except for the fact that this stuff that's on here and is the same for every C program. So the point of this program here, have you look at this is the stuff that we can understand it, and it sets up the activation record for main, but it's the same for every program. So once you realize that that's the case, you can sort of bracket it out and sort of not consider it, because we will be looking at the body of main and what different instructions are. But I want you to be able to look at this stuff and not be scared off by it. So what I've done is I've prepared in this record here, I annotated this first 0 with assembly code file here that's gotten, so when this runs, it'll run, but it won't really, I mean, I can run this, and you can run this by clicking on, I think, finish, and it'll go all the way, see, to halt and stuff. And I think finish then will see we've halted the LC3. Okay, so it goes all the way to halt, but it doesn't do anything. Now we could go through and look and see that what the return value was. But here's the code that corresponds to, you know, I've got a lot of white space here, but it's in the order of like 50 lines. So maybe it's like 40 lines of code just for the main method. Now, so what is all that code for? Well, it's setting up the activation record. Now, it's based on a memory format. Let's look at the memory format. So it's setting up a memory format. This is only part of the memory format. Let's look at that memory format for a function. So and this is true. This is how a real C program or any program works. That it has an image of all the memory. Now, in a real computer, this is a virtual memory space. On our computer, it's a real memory space. But any memory space, whether it's real or virtual, has um, all or counts for all the computer's memory space. That's why down here you have memory cell X, E, F, F, F. That's still a ways away from the very bottom. X, F, 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 because it's not quite, it's like there's a bunch of, in here, um, in this very bottom space, this is where the device registers live. Okay, now up here at the top, up to X 3000 is operating system memory. And then at the top, here's your program. And after that are global memory cells. And this pattern is going to hold both for the LC3 and for a C program and for, well, actually any program that's run on a Linux computer. And down here, this is the stack. So there's going to be the activation record for main down here. And then this memory in the middle is called a heap, because it's a heap of memory. This is most of the memory. Like this is, because your program starts at 3000, this is going to just be really short up here. But this is like those 50 lines. Okay. And it's going to include this stuff here. And then down here, you're going to have the activation record for main. So so what's happening is that the computer has to set up this whole memory pattern. Now, in a real computer, that's why executable files are a lot larger than the actual file itself, because it sets up all this stuff. Now, in a real program, a real C program, there's a lot more detailed information that has to be saved for all kinds of situations. So there's an overhead. Just running any program will use up thousands and thousands of memory cells, even if the program does nothing at all. And it's a given format. You'll see sometimes it's called ELF, executable loadable format, which is the file format for an executable program. And so that's the portion that you need to be aware of, sort of, so you have a map of this big picture, but we don't really need to this is just sort of the environment, and once we understand the environment's there, we can sort of ignore it and focus on what's actually going on with the program. Okay, so it's this situation that's getting set up. Oop, I wanted to get rid of that. Get rid of this. And always on top for this code. Now I've annotated this code to show you what each one does. Now, for example, I should explain the format of, because the format of the assembly language produced by the compiler is not exactly the same as our handwritten format. For example, here you see the .org X3000. Well, we recognize that, and why this isn't capitalized, I have no idea. Now, but here's the first real divergence. On line 2, we have a label, init code. That's the label for the following line. So so we would usually put this line 3 out over on the right, but this is a computer generated file, and so instead of since it's not intended that people look at it, it doesn't have to format it the way that for people, the way our programmers, the way we look at it. So when you see this label here, like init code, it's the label of the following line. So this line 3, this is line 3000 here, LEA R6 minus 1, and you'll recognize that as the instruction that loads itself into memory. So that now it loads it into R6. Now R6 is going to be the top of the stack. So this has got something to do with the stack. And then when it's doing something funny here, it also sets R5 to 3000, and R5 is going to be the frame pointer. So that's what's going to happen here is that R6 is going to point to the top of the frame. That means it holds, point to means it holds the address of the top of the frame. And R5 points to or holds the address of, this is the top of stack. So if this main wants to call another function, it knows where to start writing the activation record. And this is main's frame pointer. Okay. I know this is a lot of information, which is why I'm recording this so that hopefully you can, if you've missed something. This is all in the textbook, but it's not immediately in the textbook. It's sort of halfway in, but I wanted to give you the big picture. So here's the stack frame. Now, so it's building up. Now, the problem it's trying to solve here, which is a little bit mysterious, is see it has copied, you've got 3000 in R5 and R6, then it adds R6 to itself. So now R6 has 6000, it adds R6 to itself again, so it has 12,000, or C000. Then it adds R5 to R6 to get XF00, then subtracts 1 from R6. Now R6 has EFFF. Well, that's the base of the stack. So what it was trying to do, what the writer of this code is trying to do, is get this value, the base of the stack, without having to put it somewhere in memory, because there is no program yet. So there's no agreed place to put values like this. So they have to be generated algorithmically, or at least that's my take on what's going on. Now then, this next instruction is a mystery to me. It puts the value 6000 into R5, then erases it with the next line. So unless there's some complicated program or something else that uses this R5 value, at this point it seems pointless. But then at line 10 here, we have R5 equals R6 equals EFFF. So that's the goal, that initially the top of the stack and R5 point to EFFF. So now we're set up for setting up the activation record for main. Now, the next line 11, see, we have global data up here. So we need a register. R4 is going to point to the global memory here. So R4 is special. Now you see, this is a label, LD into R4 global data pointer. And I'm going to tell you that what that is 301D. So you can see it's a ways down from 3000, okay? Now, the problem is, what is the label global data pointer? Well, there it is right here in line 16, global data pointer. Now, if you went and looked at what the LC3 actually produced, it doesn't have .fill X301D. I edited that to put it in here. What it does is it has a second label, and that's the problem with, that's like sort of unusual. That works on this compiler, but it doesn't work on the simulators for their assembly language. But so here's the global data pointer, and this is going to change from program to point the value. It'll always be in R4. Okay, then then R7 is so our 4 points there, and then R7 now gets the global main pointer, which here's X300E. And this will always be the same. This code here is always going to be the same for all of our programs. So once you look at it once, you can sort of say, yeah, I've seen that. And here it is, it's X300E. And here's the main function. So there's going to be a segment of this for every function, right? And it's so the goal here is to prepare the activation record. Here's the label main. It's the label of the following line, X300E. If you count down, you can get here. Okay. Now, what this is doing here is this R6 minus 2 is leaving space for the return value. We're setting up the main activation record here. And let me get that. Well, it's 1052. So you can see that there's a lot of detail here. And what your task now is to see if you can start the LC3, type in this program 0.c, assemble it, compile it using the LC3 compiler, and begin to look at 0.asm and begin to sort of put together, try to walk through my comments on 0.asm in activation record 0. Now we're then going to go and look at a series of other programs. Like here's our first program that is 1.c, which only has one line, int a equals 84. That's a line of C, just like it is in Java. And it's going to return a number 42, so we can see this value and see where it is in code. Okay, so this is our first actual program, because our goal is to isolate what is the assembly code for this one instruction, int a equals 84. So the purpose of 0 is for you to see how to find and locate just the assembly code for this one instruction. And then we're going to continue that process all the way through, in which we're going to put in code here in C and look and see how it gets compiled to LC3 assembly language. So I haven't left much time for questions, so that is the sort of beginning stuff that you want to do, you want to look at. And so send me a message on Piazza if you can't get your all the stuff with the LC3 running, and I'll try to put these videos up on YouTube on RigX or something like that, so that you can look at them again if you need to get the information, or you can send me messages on Piazza. But your goal is to compile and you can get the simulator working, but just see how much you can get working and where you get stuck first. Okay, it's 10:54 and I should let you go to your next class. So feel free to head off. Does anyone who doesn't have to head off have any questions that you desperately need answered right now? Chris, Daniel, Emmeline, John, Jingming, and Samuel?
Oh, good. Thank you.
Okay.
Bye.
So we will see you in the lab this afternoon.
Yeah.
So we can ask questions there. Okay.
Sure.
Good luck.
Thank you too.
And I will go ahead and end the meeting so you can recover from this extravaganza.